for a rigid rotor. Now the point is, what is a rigid rotor? Now suppose I have an atom 1 and atom 2, okay? I have two atoms, and between these two atoms there is a bond, okay? The bond is such that neither of the two atoms is allowed to move away or come close to each other. You have two atoms, are you getting me? You have atom 1, you have atom 2, okay? If we think in real sense, if you have two atoms, between the atoms there are bonds, okay? So these atoms are always in motion, right? But what we assume here, we assume that you have two atoms, between them there is a distance, and this distance is fixed, okay? So you have a two-body problem basically, because you are talking about the 2-point masses. You have two atoms, you have 2-point masses at a finite separation, and this separation between the atoms cannot change. So if it cannot change, that's why we call it a rigid rotor. What we call it? We call it a rigid rotor, and we have to resolve this problem. This rigid rotor could be, you might have done it in classical physics. I don't know if you have done it in classical physics. You always go and solve the two-body problems, okay? Okay, you solve the two-body problem. Here again you have a two-body problem, but this two-body problem has to be resolved quantum mechanically, right? So if you have to resolve this two-body problem quantum mechanically, what is the basic assumption? The basic assumption is you have two atoms, 2-point masses at finite distance. And you want to solve this problem in spherical polar coordinates, right? What are you trying to do is, you are trying to resolve this problem in spherical polar coordinates. What you have, that means you have a rod and you have two atoms, okay? Now you place this rod in spherical polar coordinates, right? So how will you solve this problem? You will solve this problem using Schrodinger's wave equation. You will write down the Schrodinger's wave equation in spherical polar coordinates. Are you getting my point? What will you exploit here? That's my question. In Schrodinger's wave equation, when we write down Schrodinger's wave equation in spherical polar coordinates, we write the radial part, the angular part, and the